The final part of this section 9.6 is to go back and use our solving equation ability with rational equations to work with story problems. And here are just some typical type of story problems that come up in this realm. So we have Josephina can row 4 miles upstream in a river in the same time that it takes her to row 6 miles downstream. Her rate of rowing is in still water is 2 miles per hour, and we want to find the speed of the current. So she's rowing at a constant rate when she's going upstream against the current as opposed to downstream with the current. She's still rowing at a speed of 2 miles per hour, but there's this current that causes her to go more slowly when she's going upstream and more quickly when she's going downstream. So a couple things we need to remember is first thing is that distance equals rate times time. We know that if you move row at a constant rate for a period of time, you can determine what the distance is. So if she was in still water and she was rowing 2 miles per hour and she rowed for an hour, she would move 2 miles. Now, we know that this is her constant rate of rowing, and we have some current. The current is not, we're going to assume, is not changing. So let's say I let x equal the speed of the current. And I'll have that be in, again, miles per hour. We'll keep those units the same. We're going to deal with distance in miles, and we're going to deal with time in hours. Now, we know that she goes with the current and she goes against the current. And I'm going to make a little chart. And when we organize our information and we think of that distance equals rate times time, and if we put up our information in something like this, it does help us figure out our equation more easily. So we know that we're dealing with the distance in miles. And notice that she can row 4 miles upstream, and that's going to be against the current, in the same time that she can go downstream 6 miles. So she travels these two distances in the same amount of time. So these are in the same amount of time. Now, when she is rowing with the current, she's rowing along at 2 miles per hour, but she has this current that's helping her. So she's actually going down the river at 2 plus x miles per hour. On the other hand, when she is rowing against the current, she's rowing along at 2, but the current is hurting her. Now, we know the current cannot be faster than 2 miles per hour, because if it is, she will never go upstream. She will go backwards in her boat, canoeing, we're going to assume, if she's rowing. So, what do we have in this situation? We know that distance equals rate times time, which means if I divide both sides here by the rate, the distance divided by the rate will equal her time. And we know the time of going with the current is equal to the time to go against the current when they travel at those two distances. So the time with and the time against are equal to each other. If I take her 6 miles that she travels and divide it by her rate, that's the amount of time. If I take her 4 miles that she travels going upstream, which is going against the current, and divide it by her rate, that's the amount of time it takes her to travel her 4 miles. And we actually know that these two times are equal. Okay, so to reiterate, we know that she travels 6 miles with the current going downstream, and this is the rate she travels. Her distance divided by rate will give her her time. When she goes against the current, she can go 4 miles. This is the rate she travels. This is the amount of time it will take her. We know that those two are equal. So she can go 6 miles downstream in the same amount of time she goes 4 miles upstream. And so now I just have to solve that equation. It looks very similar to what we did before. Now I'm going to multiply through by 2 plus x times 2 minus x, the least common denominator of all the fractions. And when I do that here, These cancel, and I have 6 times 2 minus x, and I'm going to distribute. And likewise, I do the same thing over here, distribute this through. And I have 4 times 2 plus x. And when I add 6x to both sides and subtract 8 from both sides, divide both sides by 10, or I could call it 2/5. And so that is the current. So we know that the river is what we're finding. The river speed, or current speed, is 0.4 miles per hour. Now we have a similar question on number 5. We have Rosa can jog 5 miles downhill in the same amount of time it takes her to jog 3 miles uphill. She jogs downhill 4 miles per hour faster than she jogs uphill. Find her jogging rate. Now, obviously, we don't have a current, so we don't have this hill with water pouring down and causing Rosa to fall. But we do have to find, in the end, what her jogging rate is each way. Okay, and we know she is faster when she goes downhill. We like going downhill. Lot less sweat. And so we have going downhill, and we have going uphill. And we have a distance, a rate, and a time we're talking about once again. We're talking about miles. We're talking about miles per hour, and we would be talking about hours here. So I got to fill this in. I know that she travels 5 miles downhill in the same amount of time. And I know these two times are going to be equal. In the same amount of time it takes her to go 3 miles uphill. Now, she jogs downhill 4 miles per hour faster. She is faster here. So I don't know either one of these rates. I know I'm going to do the same type of thing that I did up above here with making these times as a distance divided by rate, but I don't know either one of these. But I do know that she's faster here. So I'm going to choose to let x stand for her uphill speed, and then her downhill speed has to be 4 miles per hour faster, and that's not 4x, that's going to be x plus 4 or 4 plus x. We don't want to make it 4 times higher, we want to make it 4 more miles per hour higher. And now you can see a similar setup. That distance equals rate times time, but her distance divided by her rate is another expression to describe her time. So 5 over x plus 4. And her rate going uphill, if I divide that into her distance, that's an expression for her time. That's an expression for her time. And I know that the time going downhill is equal to the time going uphill at those same distances. And these two will be the same number of hours. So I need this to equal this. So there's my equation, and now I'm ready to clear my fractions by multiplying both sides of the equation by the same value. So I have, get rid of this guy. Both sides will be multiplied by x plus 4, and I also need to get rid of that guy. Do the distributing here. X plus 4 is canceled, and I'm left with 5x. Do the distributing here, and I have 3 times x plus 4, and I'll distribute. Subtract 3x from both sides. Divide by 2. And now I got to make sure I read my question. I have to find both rates. She travels 6 miles per hour, and that is uphill. And remember what's true about downhill. Downhill, she travels x plus 4, so she travels 10 miles per hour uphill. Excuse me, downhill. And holy cow, is she moving. All right, so now the last question. This is going to be a little different, but it will be somewhat similar. Again, the idea is we're going to end up with some type of a rational equation, something that's going to have variables in the denominator, some expression with variables. So we have Anita and Fran have volunteered to contact every member of their organization by phone to inform them of an upcoming event. And Fran can complete the calls for this big list, however many there are, in 6 days if she does it all by herself, so that she can finish the job in 6 days. Anita, on the other hand, can complete the job in 4 days, so she must not talk as long, call more frequently, and get the job done faster. But what are we going to do? We're going to have them work together. And we want to know how long it's going to take for them to finish the job if they work together. So we are going to look at their rates. And this is kind of similar to this current problem. If you have the rate of the girl being able to row by herself and the current, the sum of those two is the rate at which they go together. And we're going to have the same idea here. We're going to look at Anita's rate at which she can get a job done. We're going to look at Fran's rate. And then we're going to look at their together rate. And we know that Anita can get one, and I'm going to call it a job. If we knew how many phone calls and so on it was, we could actually put that number up there. But we really don't need to know that. We know she can finish one job of calling all the membership, and she can do that in 4 days. Fran, on the other hand, can call and get that one job done in 6 days. So Fran gets 1/6 of the job done per day. Anita gets 1/4 of the job done per day. So that's the rate at which they get a job done per day. Now, when they work together, they're going to get one job done in, and I don't know how many days it's going to be, but that's my variable. If we take Anita's rate at which she can get the job done, and we take Fran's rate, that will equal their together rate. So Anita's rate in jobs per day plus Fran's rate in jobs per day will equal their total rate in jobs per day. There's my equation. And so if I think about what the least common denominator is of all those fractions, it's looking to me like it's 12x. So if I multiply everything through by 12x, when I multiply this factor by 12x, I get 3x. When I multiply 12x times 1/6, I get 2x. When I multiply 12x times 1 over x, the x's will cancel, and I end up getting 12. So I get 5x equals 12, or x is equal to 12/5, which gives me 2 2/5. And what am I trying to find? That's how many days it takes 2 2/5, or 2.4 days, to finish together. And I see lots of glare there, and now it's coming back. There we go. So it takes 2 2/5 days to finish together. Right, and then your questions, again, will be modeled something similar to the ones that we just looked at. And you're ready to practice.